Welcome to Walkabout the Galaxy, the hopeful astronomy podcast, where the science is universal, the opinions are personal, and the hosts are relentlessly positive.
Hell yeah.
We are Strange,
like
Charm,
that.
and Top the Astroquarks, also known as Josh Caldwell,
Addie Dove.
And Jim Cooney.
coming to you from physically but not socially distanced locations near the University of Central Florida. Remember to check out our website to see how to get our snazzy shirts and subscribe to us on all platforms, including YouTube, where you can catch our first and soon-to-be Grammy-winning music video, the Astroquark song. Let us know what song you would like to hear and see Quarkified next using hashtag AskWTG. Also, stay tuned for an upcoming episode to be done as a musical.
Oh, no.
Yes. Think Les Mis. Totally no spoken words.
Well, I was thinking of Buffy, the episode of Buffy where they did a musical episode.
Okay. There you go. So
it
sounds like Addie's down for it.
Episode of every show is it's the one
musical episode.
They did that.
That's incorrect. That is incorrect. That was a very good episode of Buffy.
Fair enough.
What did you say? It's not your. It's your least.
It's my least favorite.
Jim doesn't like musicals.
I don't like musicals. I'm just going to say it. I don't. That doesn't mean I have anything against people who like musical theater or musical theoreticians or whatever. But I don't get it. Just say the thing. Stop singing it.
Aw.
I'm sorry. I know that's an unpopular opinion.
How do you feel about Disney movies?
No, not if they're singing.
So let me just get this. Let's just sum up here. Okay. Like stamps, early morning fishing contests, hates music.
No.
Likes physics.
Josh, you don't like jazz. Should I also say you hate music?
No, because I like music.
Well, then you can't say that about Jim.
Yeah, I like music. I don't like musicals.
He doesn't like when people are singing stuff, sounds like.
It's weird. It is weird. I like theater and I like music. I just don't like musical theater. Sorry.
That is weird. Okay.
Weird. Anyway.
Well, anyway, we're doing it. So you're going to have to
fair enough.
Get over your problem.
Okay.
Our stumpers today are vehicular. You can place your vehicle in any context you wish, but since it's a space astronomy podcast, you may want to bear that in mind. So your vehicles, Jim, copter or balloon?
Now see, if this were terrestrial, my answer would be clear, balloon.
Oh, okay.
But if this is extraterrestrial, then it's copter. I like balloon. Like if I had to go for a ride in one, I would go for a ride in a balloon because I hate noise and choppers are very loud.
They're also deadly.
I guess they're, yeah. I mean,
so are balloons.
I'd be
drop out of the sky.
Yeah, to be clear, I would be terrified and weeing my pants in either one, but because I'm a wimp. But a balloon is a nice, quiet, beautiful ride.
I think that when they pull when they're like firing the
that's probably loud,
flamethrower up in there, I think those are quite loud actually. You're standing right next to a giant freaking flamethrower.
That's kind of awesome.
Yeah.
That's kind of awesome. But when they're not doing that and just hanging out, it's got to be nice and quiet, right? I mean, I don't know, other than ear noises. But yeah. But if I'm talking about going on to other planets, having the ability to control your trajectory a little bit better is cool. So I want to be a
I would be, okay, glad I asked. I would have been the exact opposite. Copter on the Earth, balloon on Titan or Mars or something. Get to see more. You get to drift around. Every place is going to be new and interesting. So,
all right. Okay.
Yeah.
Cool.
Addie, yours are submersible or rover?
I guess I'm probably going to go rover.
You're a little bit more limited with the submersible than a rover, I suppose.
Yeah, I mean, you can't take a submersible on the moon or Mars.
Right.
Yet.
But you could, if you were willing to go deep, you could
Titan.
on Enceladus and
it's true.
Europa.
I would love to go in a submersible on Earth, like go on one of those dives. That'd be super cool.
Okay.
But I would also like to go on a rover on Earth. So.
Oh, I think those can be arranged, actually.
I think so. Yeah. There's this commercial right now for maybe it's T-Mobile. It's one of the phone companies where they're driving a rover around on the moon. Have you guys seen this one?
Yeah, look fun.
Yeah, it's mostly fun and it's mostly okay. They like do some things where it's clear there's low gravity and you're like, okay, sure.
They were
But then
doing
at the
some pretty
end,
dangerous stunts with that lunar rover on that
and
commercial.
there's no roll cage or anything. It's a little
Yeah.
dicey. And then at the
Yeah.
end, the phone flies off and it just floats there.
Oh,
It ruins it right at the end.
ugh. They should have hired us to consult.
Seriously.
Yeah.
But speaking of balloons and musicals, we've been watching His Dark Materials, which is a show that's
Yeah.
based on like the Golden Compass series, I think.
Yes.
It's really a show. I like it a lot. But there's an aeronaut, and it's played by Lin-Manuel Miranda from Hamilton fame.
And what sort of vehicle does the aeronaut use?
A balloon.
Okay. Well, today we'll talk about sextuply eclipsing sextuple star system,
All right,
because we get to say sex several
PG.
times.
I feel like that's redundant.
Also, well, it's not actually redundant, so it's surprising.
Okay.
Also, rumbling from galaxies that doesn't have anything to do with sex, and the
Sextuples.
or sextuples, any kind of couples or upples, and the lakes on Titan. But first, this episode of Walkabout the Galaxy is brought to you by the band gap. Are you feeling overwhelmed by the constant din of electrons banging around in the conduction band? Have the once melodious tones of the valence band gotten on your nerves? Take a break from the original electronica music and step into the band gap. In this unpopulated energy realm, you'll be free of current and insulated from the push and pull of electric fields, not to mention your friends' constant hectoring. For calming the mind, there's yoga, but for calming subatomic electrical activity, there's nothing like the band gap. For best results, use the band gap at low temperatures. Band gap, imagination at work.
Very nice. You went far afield this time to like condensed matter physics. So we're all part of the physics department at UCF, but we rarely venture that far afield.
Yeah. Well, this is episode 223. So we've had a lot of sponsors.
Sponsors are coming out
Should
of
we
the
be worried
woodwork
that none
now.
of our sponsors ever repeat? That's concerning to our bottom line.
No, it's
No.
fine.
Now we're
It's
casting
still the same bottom line.
That's right.
Maybe the band gap can help with that, actually.
Maybe. Imagination at work. Any thoughts?
That's so general. That could be.
Is it Play School? Mattel?
Oh yeah.
Oh,
Good thing. Legos.
no.
Yeah.
Yeah. It's General Electric.
Oh, okay.
I was trying to look for something from the store, The Gap, but
I thought you were going to use either the Gap reference or like Mind the Gap or something.
yeah, I was looking for something like that, but just like they were too obvious. They were like, get your clothes at The Gap. So
they have some like seasonal
JCPenney?
slogans sometimes, but yeah.
Let's see. 143 satellites were launched on a single Falcon 9 yesterday.
We were just talking a few episodes ago about what the record was, and now it's changed.
It's a new record. That's right.
A new record.
So these are all.
And I think they all deployed okay.
These are CubeSats, right?
Not
Not all
all
of them.
No.
No,
There
they
was
were
like
of
a
all
couple
different
of
sizes.
main satellites that were bigger, and then a bunch of CubeSats.
There were 10 of them were Starlink satellites, which are pretty hefty satellites. So that's SpaceX's Wi-Fi service. And so this launch was unusual. It's from here in Florida, and we can see those from Orlando. And I'm used to seeing those things heading off to the north. But this one headed due south, which was we were like, why is it going that way? It's made a wrong turn, because we don't usually see those kinds of trajectories, but it's a polar orbit, and it's a new shell of the Starlink satellites that they're starting to populate. And they now have more than 1,000 of those in orbit, which is kind of incredible.
Yeah.
So
I wonder if they were like, they had this mission and they were like, oh, we have all this stuff. We have a tiny bit more room. Let's throw on some stars.
Yeah.
Of those 143, how many were you guys?
0.
Oh, man.
0.
Yep.
Although there were a bunch of Planet Labs Dove satellites, so I was like 6 technically.
Oh, they're yours.
I think there were like
Okay.
6
I'll give them to you.
We'll call it. Okay, there we go. The next test flight of the Boeing Starliner has been scheduled in an almost unprecedented move to be 4 days earlier than it was previously scheduled,
Ooh.
March 25th. So as we recall, back in 2019, the first orbital test flight of the Starliner did not go entirely as planned. There were some software issues, and so this
That was
is,
in 2019.
it was,
Oh wow.
yeah. So this next test flight will, like the first one, not have any people on board, but hopefully they've resolved all their issues. And then if this one goes well, then there will be a crewed test flight of that vehicle to take people up to the ISS, like we had with the Crew Dragon last year.
Yeah, and that one was mostly the test flight. It was mostly software issues, it turns out.
Yeah,
And it was enough that there was an issue and it didn't get quite the right orbit, so it came back early. And it turned out like a few months later, they revealed that like, oh, there could have been something really bad that happened on reentry, but they corrected it in time. And so, yeah,
yeah,
there's lots of Boeing has had a rough time with their software, but I think they're coming back on both
yes,
the plane end and the Starliner end.
yes. Hopefully all these, and that's, why there are test flights, work
Yeah, for
work
sure.
these things out. Yeah.
Yeah,
Uh,
they've announced, I don't think they've announced yet if they're going to do another, speaking of tests of the SLS engines before they do like a full-on test. But I think most people are like, they were saying they may not because they can only do so many tests with those engines.
right. I think it's
But
the
like most people are
tanking,
like, nah, you should
actually.
probably do a test. What?
Yeah, I think the limit is not the engines so much as the tanks. So the SLS
Oh,
is the
okay.
Space Launch System, which is NASA's new heavy lift vehicle, where it looks sort of shuttle heritage. So the shuttle had these two solid rocket boosters on the side of a big tank, and then the shuttle itself had three engines, and that got their fuel from that big orange tank. So the SLS has a sort of central core stage, which is a traditional kind of rocket core with tank of oxygen and fuel, and four engines at the bottom. And then it has two even bigger solid rocket motors that'll go on the side of that. And then on the tippy top will be, one of this little Orion gumdrop capsule. So much, 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 much smaller than shuttle, a little bit bigger, I guess, than the Apollo capsules, but still pretty small. And so
That'd be
they did
terrifying sitting on that much explosive directly below you.
that'd be quite exhilarating. Yeah. So I think we mentioned on the last episode that they did what was supposed to be an 8-minute test firing, full duration test firing of that central core stage, and it shut down after a little over a minute. And then, as you were saying, Addie, there was some sort of conflicting information flying around about how frequently they could do it before, like, they ran into the limit of the number of times they could use that particular thing. And I
Yeah.
think the limit was on like pressurizing the tank,
Okay.
because when
Hmm.
they fill it up with all that stuff, that's putting some physical strains on all the welds and everything that are in
Yeah.
there.
Yeah.
So I think that's what the limit was. And at one point,
Hmm.
it sounded like the limit was 9, and then I heard it was 22.
Oh yeah, I definitely heard the 9. I have not heard the
Yeah,
22. So those are
yeah,
different things.
they are very different. So I think that they they
Even for an
maybe
astronomer, those are very different numbers.
that's right. Yeah.
But
Definitely
order
for a
10.
rocket scientist, they're very different for
Yeah.
sure.
Yeah.
So they'll probably do, I hope, well, I'm sure they'll do whatever is the appropriate thing to do. And you'll hear all about it whenever they do or don't do it on Walkabout the Galaxy. Our first little news bit is from a mission near and dear to my heart. Can you guess?
Probably Juno.
Ugh,
Yeah.
gosh, you
Voyager
guys, come
2.
on. Hey, it's
Is it
Cassini.
is it Curiosity? No.
So,
Cassini?
well,
Did you work on
in all
Cassini?
seriousness, one of the things that I think a lot of people who are not in the biz don't understand is that the work of the mission doesn't end when the spacecraft or the observation collecting aspect ends. So this is true for like ground-based astronomy or space-based astronomy. You take the picture and it's not like the next day you're all done. Oh, you got your picture. Here's the picture. There's a black hole. End of story.
Right.
And it's the same with spacecraft missions. Those things go, and for some, maybe for days, maybe for weeks, maybe for years, collect data, and then sometimes the mission ends dramatically. The spacecraft, in the case of Cassini, burns up in the atmosphere of Saturn. Other times it ends less dramatically. It's like, we've lost contact with such a spacecraft, or the Mars rovers run out of power and we're, not going to talk to it anymore. That's not the end of what we learned from those things, because while we're running the mission, we're like so busy collecting all this data, and it takes a lot of time to analyze that data and figure out what exactly it's telling you. It involves doing sophisticated models, physical modeling of whatever it is you're looking at, and then trying to adjust that so that it matches your data and so forth.
And you have some of that sort of pipeline established ahead of time where you're like, well, we know what we're going to expect to see and we can process the data in some ways. But then over time, your techniques improve, your understanding improves, models change, right? And so you can actually like improve that. And then just like new people come online and have different thoughts and come at it a different way.
Different techniques, different abilities, and different tools. So yeah, absolutely. So
and most NASA data is archived online so that any of us can access it. Technically anyone can access it, but like usually you would write a proposal or something to continue doing data analysis long after a mission is over. People are still analyzing like Venus data, right, for Magellan.
Yeah. And I mean, the data truly is accessible to everybody in the world. I mean, for our field in planetary science, the planetary data system, those websites are open and you can just download that data. They're available. Frequently it requires, some training or work to understand what the heck you're looking at. But the data is available. So this particular study that just came out in Geophysical Research Letters is talking about probing the depths of the lakes on Saturn's moon Titan, one of our favorite places in the solar system, and a place where Jim would like to fly a copter, right?
Yeah.
Which is gonna happen.
Do I get to fly it?
Which is kind of amazing.
Yeah,
They
awesome.
NASA previously, as we've mentioned, selected a mission called Dragonfly, which is led by one of the Cassini scientists from the Cassini imaging team, to fly around in Titan's thick atmosphere. And it's a pretty big, it's not like one of these little quadcopters like is going to Mars, that's actually landing next month, right? With Perseverance rover, it's carrying a little copter
on Mars, yes.
to Mars. That one's just sort of like a little tech demo. Mars' atmosphere is super, super, super thin. So you have to have a really lightweight copter, and the
little carbon fiber, tiny little RC copter.
And the thing has to be spinning, super fast. Whereas Titan, the gravity is much less than on Mars, and the atmosphere is so much thicker, so you can do a lot more. Anyway, or you could take a submersible.
Or you could take a submersible. Cool. And in this case, you can take it pretty deep, it turns out.
Titan is maybe the only place in the solar system where all four of those vehicular options are available, except the Earth, obviously.
Except the Earth. Yes.
But copter, balloon, submersible, or rover. Anyway, Titan is super cold. So on Titan, natural gas is a liquid. Methane is a liquid. So you wouldn't pass gas, you'd pass liquid.
I was just thinking about that and how gross that is.
Oh, that's messy. Oh, okay.
Sorry.
That was literally,
I'm so sorry.
Yeah. I was like, am I going to say anything? That's going to be a gross one.
I'm a little bit sad that we both thought about that, but also a little bit relieved.
Not as, well, never mind.
Yeah, but not really relieved. I'm not really relieved.
Yeah.
Anyway, it has lakes of methane and ethane, and
now we know how they got there.
During the Cassini mission, they flew by Titan several times and did radar measurements, and by looking at the echo of the radar, we're able to measure the depth of some of these lakes. And Kraken Mare is the deepest of those lakes. And we knew that it was like at least about 100 feet deep. Now it looks like it could be more than 10 times that deep, more than 300 meters deep. And most of the volume of liquid stuff on Titan is in this one large lake, Kraken Mare. And there are parts of it that sort of this lake level, I was going to say sea level, rises and falls because there's an island that we saw that appeared and disappeared, got covered up partly during the mission. And so that would be super cool place to visit, I think.
Yeah. And they have big error bars on this because they actually, from the radar, so radar is tricky because, right, you're not just looking, and I don't know, we always think about like looking at things and you see, okay, there's a difference between these things. But radar, it's like it bounces off things differently based on their dielectric properties, but like their material properties, right? So like it's going to bounce differently off the surface of the lake versus the bottom of the lake. But they don't think they got a radar return from the bottom of the lake because it's so deep. So they used some estimates based on an estuary, a sort of narrower part that was in itself pretty deep.
Right, over 100, like 100 feet deep. Yeah.
Yeah, to figure out how deep they thought then the rest of it must be.
Yeah, so they like if you can see the echo from the bottom compared to the echo from the surface, then you can look at the timing difference and use the light travel time to figure out how deep it is. But as you're saying,
and
it
also
depends
the
on what that
materials
stuff
it might be made out of. Yeah.
Right. Yeah. Because the propagation of that radar light through the lake is different depending on what exactly it's made of. So they had to figure out what the stuff is made of, then fold that into how far, what the propagation through the deeper parts of the lake would be. So that's kind of cool. The lot of interesting questions still remaining for Titan. It's 10 times further from the sun, so it's a lot colder. It doesn't get as much sunlight, and there's still a big open question about how the methane is sort of surviving on the surface. So you can calculate the lifetime of methane sort of photochemically, and the lifetime of all the methane that we know about on Titan is much less than the age of the planet, so that presumably there's some sort of source from the interior coming out, or we're looking at it in an odd, non-representative part of its history. So more to come still from the Cassini mission.
I'm going to have to warn Bottom Cork not to watch this episode because she is absolutely terrified. Apparently this is like a common thing of big, deep water, cold. This is, of course, water, but it's similar.
You should not watch the movie Underwater then.
No. Well,
I think we tried to get her to watch that. Oh, now I regret that.
She won't. Yeah, she won't. But she'll be terrified of very deep methane lake that's cold and big and super deep.
Yeah.
Okay. Well, we'll make sure not to recommend Titan for a vacation, or at least not the Kraken Mare.
You would not choose submersible for sure.
Oh,
okay. Yeah. I totally get that. I totally get the ocean is terrifying. It's
Would you rather go to space or the ocean? I think we've had this as a stumper.
I think I would rather go to space, although there's no rational argument. I mean, I know I would. I don't know. I would rather go to space, but there's no rational argument for being less terrified of space than of the ocean.
Yeah.
Except that there's no fish in space.
The fish aren't the scary part of the deep ocean.
Josh, it's named Kraken Mare for a reason.
Oh yeah,
their realm. It's like that's their place.
Their place. Okay.
They know what's going on there. Anyway, let me tell you, since I don't know, I feel like we've gotten a little bit into this area with the depth of the lake. Let me tell you what our trivia is going to be before we talk about.
We've gone off the deep end.
There you go. That's very much relevant to the trivia, which is about funny units.
Ooh, I like it.
So we throw around sometimes lots of units when we're talking about whatever the heck it is we talk about. I'm going to give you a list of some units, and you're going to tell me whether or not they are quote unquote real. And to determine whether it's real means if you enter it into Google and say, convert one of these things into something else that's got the correct dimensions, whether the Google conversion calculator accepts that unit, all of them it will give you something because Google search engine will send you off to some website that refers to it. But if Google has adopted it as one of its units for that dimension in its unit converter, then it's real. And then, of
So
course,
this isn't like real versus fiction where there are also units.
I mean,
Just random stuff that you came up with.
I did not make any of these up, but these are
Okay.
all, but somewhat unusual units. So you're going to
Okay.
be determining whether or not the Google unit converter considers it a real unit, and also you're going to figure out like what it is, what kind of unit it is,
Okay.
and how big it is.
Got
Some
it.
of those will be obvious,
Okay.
maybe. Some of them will be obvious and some not. So I'm going to list. I got about
Do
8 or
some
10 of these units
dimensional
here.
analysis
So
on
I'm
these.
just gonna drop these units on you, and then we'll come back to them at the end of the show. Ready?
Don't hurt us.
Yeah.
Okay, here we go. We'll start with the barn, then the attoparsec, one of my favorites, the beard second, a shot, a shake, a jiffy, a galactic year, a hand, and a quad.
I feel like
So-
we're playing Balderdash or dictionary or whatever you want to call it, and we get to make up our own definitions.
That's
for
right.
these. This
There
would be
you go.
that would be a fun round. Is like actual units
That's
that are
right.
things. Yeah, that'd be
Yeah.
a fun round.
Yeah. So
I have some good definitions for some of those.
yeah. Anyway, so we'll come back to those and see if you can figure out whether you know any of them. I think some of you, all 2 of you there that I'm speaking with.
And in the audience,
There
some
are
of you,
so many listeners out
there are
there.
so many people with us right now.
some of you will know some of these,
Perfect.
but I'll be surprised if both of you know all of them. See.
Yeah, I would also.
Let's
All
look
be
at the Venn
surprised.
diagram here.
So with that, Jim, let's talk about and Addie, what we can learn about gravitational waves from. Where were these things coming from? Was it
Space.
Arecibo measurements are related to these because these
No.
are no?
Radio.
Yes.
Yeah.
Yes.
This is pulsar timing stuff. So this was, I think we've mentioned this before, but this is a fun other way to measure gravitational waves. Measure gravitational waves isn't the right word, but to detect gravitational waves. We've talked lots about LIGO and the gravitational wave observatories and their discovery of gravitational waves coming from colliding black holes.
We measure gravitational waves. I mean, that's what LIGO does. It measures them. It not only detects them, it provides you an amplitude and
I thought you were going to yell at me for the grammar there, because like you measure a property of them, you don't measure them. You measure their amplitude or their frequency or something. You don't measure them, right? Or
I'm definitely a pedantic jerk for many things, but this one is not one that's got me riled up here.
I thought I was going to get railed there, but anyway, okay.
Sorry.
Okay.
Oh man, my reputation is terrible here.
But there are other potential ways to measure to detect gravitational waves, and this is one of them. So the idea here is this would be a different source of gravitational waves. The ones we can detect at LIGO are things that are like 2 stellar mass black holes colliding. A 10 solar mass and a 20 solar mass black hole collide, and they produce gravitational waves that we can detect. But there are other black holes, the supermassive black holes, the very scary ones that live at the centers of galaxies. And when galaxies collide, sometimes those supermassive black holes interact. And those interactions would be much slower, right? So instead of like 2 small black holes spiraling in and colliding, you have 2 big, giant, lumbering black holes slowly orbiting each other. Huge amount of energy involved. And so they do produce gravitational waves with lots of energy, but very much lower frequencies.
Let's put some numbers on fast and slow here. You used those. Sure. So like the 10, 20 solar mass black holes, how fast are they moving around each other, right? When we're sort of like seeing that, because those wave signals we get are just like a second long or something. We see the and
Right.
the
That's right. So
smack
you're seeing this
together.
the whole wave in a fraction of a second. So it's, you know, these the waves are, the frequency of the waves are many waves per second, right?
But in that time, like, does that mean in 1 second those two black holes actually physically orbited each other multiple times or something?
Yeah. In the
Okay.
last bit, yeah.
Okay.
Whereas these, and you can work out how long it takes. These gravitational waves are like nanohertz gravitational waves. So that
Oh,
means the
fancy
frequency.
unit.
Yeah, it's a fancy unit. Nanohertz is a billionth of a hertz, right? So it takes a billion of them. No,
It takes 1 billion seconds for the things to go around.
right. It takes a billion seconds for the things to go around. How
And
many
so
years?
as we all know, there's 31,550,000 seconds in a year. So that means there's 30 years or 300 years. 30 times 30 is 9,000. So 30 years.
30 years. So yeah, I mean, this is these two big guys orbiting each other once every 30 years. And this, you can see why in some respects this is going to be a much harder gravitational wave to detect, because that means that very, very slowly, right, are these gravitational waves passing you. So it's not like, you know, I look at these two mirrors, they go apart and close and apart and close and apart and close, and it's happening very quickly. It's happening ridiculously slowly. So you'd think I have to watch this for decades in order to see this gravitational wave pattern, right? Well, you do, it turns out.
Yeah.
And one way that you can do
Great.
that is by looking at pulsars. So pulsars are the dead husks of large stars.
They're so much more exciting than that.
They're much
Yeah.
more exciting than that. They're spinning neutron stars, right, which are blasting out bits of radiation in our direction at very regular intervals. And the beautiful thing about them is how regular those intervals are. They're ridiculously precise pulsars. They pulse every, you know, each pulsar is unique, and so, but they stay at the same pulse rate to a ridiculous level of accuracy. But what we suspect is that if there's gravitational waves passing, that if we look at pulsars in one direction in the sky and pulsars in a different direction in the sky, that their timings will be altered by different amounts. Because it's not just space that is warped as a gravitational wave goes by, it's space-time, right? Einstein loves space-time. So the time it takes those signals to reach us will change based on how the gravitational waves passing us. And so if we look all over the sky at pulsars all over the sky and watch their timings over the course of decades, we should be able to see slight differences in what happens in this direction versus that direction. And there's a group called, what is it called? Nanograv?
Nanograv. North American Nanohertz Observatory for Gravitational Waves.
That's right. And so this is an organization of a bunch of scientists from a bunch of different places using data from a few different telescopes. I think notably with this collaboration, it's the Green Bank Telescope, which is a big radio telescope in West Virginia. I think it's the world's biggest movable radio telescope that can point in any direction in the sky. And the Arecibo telescope, which of course just recently met an unfortunate demise, but there's still lots of data from it. So this is data from the last 12 and a half years from these things, looking at pulsar timing. And what they found is not a definitive gravitational wave detection, but a very significant hint that it is there, which is really cool.
Let me ask a question about what you were saying earlier. So suppose I've got two supermassive black holes lumbering around each other once every 10 or 20 or 30 years or something like that. Mm-hmm. And they're producing from that location this very low, slow oscillation in space-time.
Right.
And I look at a pulsar in one direction that's maybe closer to them, and I look at a pulsar 90 degrees away from it, and those waves will be hitting those pulsars at different phases or something like that. Is that why I'm seeing a different frequency, or I'm seeing that?
It's largely that, I mean, like, so that pulsar is 100 parsecs away, right? Well, when the gravitational wave is passing, now it's a little more than 100 parsecs, right? So now I'm going to see the frequency of the the light coming from the pulsar stretched out a little bit because this
So I'll
distance,
see, so over the course of 10 years, I would see, because the wave is so
slow,
slow,
subtle change, and
I would see a trend in the
right,
timing of that pulsar, and
right.
some other pulsar would see a trend, but it would be not necessarily in the same direction.
Right, that's right. So that's what they're looking for is these subtle drifts in the timing of the pulsar as these gravitational waves slowly pass us by. The trouble, of course, is that we're not really looking for one gravitational wave with this technique. We're looking for the total sum of all the gravitational waves that are passing, coming from
Yeah.
all different directions, because it's not just one, galaxy center where this is happening. We expect it to be happening kind of in lots of places all over the universe, and
Right.
you take waves and add them all up from a bunch of different sources, you get complicated gross waves, right? And that's kind of what we're looking for here. So we definitely are seeing these drifts in the timing of the thing, and it's hard to pin down what the source of the drifts are because there are lots of reasons why the timing would change.
How many different
example,
pulsars are observed for these things?
That's a good question that I don't know the answer to. I want to say a few hundred, but I don't. It's on that order, but I could be wrong.
Okay, that's good enough for astronomical work.
Yeah. But yeah, they've been able to rule out things like dust getting in the way, because like you said with the
freaking dust
in
always dust,
on
man.
Titan, light travels at different speeds through different media, right? And so if you have a bunch of stuff in the way, that can affect a pulsar's timing as well, right? Because the light travels more slowly through the stuff than it would through empty space and so forth. So you have to watch all of that stuff, but they've been able to rule out most sources, and they think the most likely remaining source is background gravitational waves. So that's kind of awesome. We still need some more data for this because they weren't able to actually claim a detection of a gravitational wave. They have like a 2 sigma detection, which in science is not good enough. Right? You need 3 or 5 sigma or something like that, meaning it's 2 sigma.
The error bars are large compared to the signal, sort of.
Right, basically.
Yeah.
So anyway, this is a tantalizing hint that we are seeing gravitational waves from all these things, although there is still work to be done. But that's kind of awesome that gravitational wave astronomy is taking huge strides forward. It's not just LIGO. Now we have other ways of seeing them as well. Pretty cool.
Yeah. And it was 45 pulsars that
45
have like the best timing and that had the really long data sets for the analysis.
Okay.
And they see this like low frequency feature across all of them.
Okay.
Pretty cool.
Interesting. So with Arecibo gone, does that end this particular experiment?
Kind of. So not entirely. They still have West Bank, and there are more groups than just Nanograv working on this kind of thing. There's more radio telescopes. China's doing some stuff with this. India's doing some stuff with this. There are some big radio telescopes working on this as well. So it doesn't end the project, but it certainly hamstrings a little bit the effort. Yeah,
I mean the data sets for Nanograv are from GBT, Green Bank, from Arecibo, from the VLA. I think FAST is actually going to be the Chinese telescope is actually going to be a part of it, and some others. But like the problem is, right, if you have sort of the same data set from the same telescope for a long time, there's certain frequencies that you have it at, and there's just certain like data analysis that's part of that you want to sort of keep as the same telescope for a long time. And I think that like, right, FAST is going to look at a different part of the sky than Arecibo looked at. So like, depending on, and Arecibo is far more sensitive than most of the other parts in this hemisphere, for instance. So like, we might lose a decent amount of those sources, but I don't know off the top of my head which one. And I think that Arecibo probably had some of the longest observations because it's been going for so long.
Been going since the 70s,
yeah. Well, before we get your units answers, I promised the explanation or the discussion of the sextuply eclipsing sextuple star system.
You promised that mostly to yourself.
So this comes from our friend, the Transiting Exoplanet Survey Satellite, TESS, which is looking for exoplanets eclipsing stars, but of course it sees things that aren't just exoplanets. In this case, it's just a sort of quirky system. It's 6 stars. It's a system of 6 stars. We've talked before about how frequently you see stars coming in pairs and sometimes with three. The sun, you know, it's not like super peculiar to have a star by itself like the sun, but a lot of systems have multiple stars, but this one is 6, and it's actually 3 pairs of binaries, 2 very close inner binaries. So it's like a quadruple system in the center orbited by another pair. So you have 6 total that are orbiting the center of the galaxy together, about 2,000 light years away from us. And so seeing a system of 6 stars is unusual for starters, but also these 6 stars eclipse each other from our perspective on the Earth, which is, you know,
So we're
maybe
seeing
a
it
little
right
bit
along
surprising.
sort of the
So all
disk
6
of
of
the
them are in
system.
roughly the same plane?
Yeah. Now the inner
That's
ones are
crazy.
so close that I don't know. They're so close that I don't know, you know, how planar they need to be in order for there
Sure.
to be some eclipsing going on.
Sure.
So it's sort of a fun thing. The third binary, the outermost one, orbits the inner 4 every 2,000 years or so. The inner 4 are so close to each other that you would not want to have a planet there. Unless you were in the movie Interstellar, that's totally where you would go looking for a planet, because that movie made no sense. But the outer ones, sorry, I don't know what took over me there, Jim. But the outer 2 binary are far enough away from the inner 4 that, you know, you could potentially have a planetary system there. So it's just sort of a fun, unusual identification.
Sextuplets are unusual, but they're glorious. So
we are still talking about stars, right?
yeah, stars.
Okay.
Stars.
Okay. Just making sure. Yeah.
All right.
Okay. So let's hear what you think
There
about these.
are 17 previously known sextuple star systems.
Wow.
That's
Surprisingly.
yeah. That's a
Pretty
lot.
cool. Yeah.
But in a galaxy of a few hundred billion stars, not so
Yeah.
many. Of course,
Yeah.
not that
So
we've
many
seen
questions about how they form and stuff.
Yeah.
Kind of fun.
Okay. Here's your units. Let's start with the quad.
Okay.
Quad.
Real or not, and what kind?
Not real.
Real.
It is real.
Damn
It's a real. It was even in my Physics 1000 textbook for my course I taught last semester. The quad.
Really?
Yes.
Oh.
Then this is embarrassing, but I've never even heard
I
of
am
it.
embarrassed for you, Jim.
Thank you.
Yeah.
Wow.
Addie, do you know what kind of unit it is?
Energy.
It is.
I'm guessing that based on what class you taught last semester.
That's right.
That's very clever. Yeah. Yeah.
A quad is it's some big number. It's a quadrillion British thermal units.
I was gonna say, is it a quadrillion something? And
It is.
Okay.
It's a quadrillion British thermal units, which works out to 1,000 quadrillion joules roughly, and that works out to the human energy consumption in the United States is about 100 quads per year these days, and several hundred quads per year for all people on the planet. Okay, let's see. So it's Addie 1, Jim 0. Let's go to the shot.
That's real.
Fake.
It is also real.
Figured.
So Jim, you tied it up. Can you tell us what kind of unit the shot is?
I want to say it's weight or mass.
Addie?
Time.
Come on, you guys. This was I psyched you out. It's just like a shot glass. It's a shot.
Oh.
It's 0.1875 cups.
Okay. It's a volume. All right.
All right.
It's like 1.5 ounces.
A beard second.
I feel like Brendan would know about this one.
Fake.
Real.
It is accepted in the Google converter, units converter. You can convert 1 beard second into what kind of unit? A unit of?
Mass.
Length.
It is length, like a light year.
Yeah.
It
Like
is.
how much a beard grows in 1 second. Yeah.
That's correct. Do you have any guesses as to how
What?
much a beard does grow in 1 second? That's what a
Jeez.
beard second is, the length that a beard grows in 1 second. And
5
the
microns.
Yeah, I was going to guess on the order of microns also.
It's 5 nanometers
That makes more sense.
in a second. Yeah. Okay.
I was gonna make some sort of James Beard joke.
A shake.
Like something about how fast you have to eat something. Anyway.
A shake. Yes.
Real.
It is not.
No.
Dang it. I was going with they're all going to be real.
But it should be. It should be. But it does.
Rattle
But
and
it's
roll,
so
isn't
it's
it?
not real in the sense of the Google converter accepting it. But it is you can Google it and it's got a definition according to somebody, and it's a unit of what?
Time.
Time.
Acceleration.
As in two
No
shakes
time.
of a lamb's tail.
Yeah, that's what I was thinking. Yeah.
So it turns out one shake of a lamb's tail, that lamb's tail is really twitching very rapidly, is only 10 nanoseconds.
What? That's
Like a
stupid.
pulsar.
I don't know.
How many?
I don't
We
know.
can start talking about pulsar timing in terms of the shakes.
Yeah. Okay. I'll just give you a couple more here. How about a attoparsec?
Real.
It is real. It sort of speaks for itself. Atto is a very, very short prefix, right?
Yeah.
10 to the minus,
I feel like we talked about this one for something recently.
and not the attoparsec.
Really?
Why would we? That's very arbitrary.
It's a very strange thing
Idiotic
because
way to
atto,
measure distance.
yeah,
Yeah.
atto is very, very tiny. It's 10 to the minus 18, and a parsec is very, very big. It's 3.26 light years. Turns out that an attoparsec is about a little over an inch.
I was gonna say. I was trying to figure that out. Yeah. Okay.
Yeah.
So it's
About an
like it's
inch.
it's a fraction. You know, it's like taking a light year and scrunching it down to an inch. All right, your last two. The barn.
Real.
It is. Do you know what it is?
Energy.
Force.
It is cross section used in particle physics, as in you could hit the
Okay.
broadside of a barn.
I knew that.
But it's actually-
Oh.
It's 10 to the minus 24 square centimeters. But if you're talking about collisions in a subatomic, particles accelerator,
As I
it's
do.
huge.
Ah,
You definitely hit the broadside of a
I
barn.
see. I get it. I get
So
it.
it's a unit of cross section. And your last one is the hand.
Real.
That's real, and it's just what it is. You use it. It's, I guess, just used for measuring horse heights for some reason. It's 4 inches precisely. 4.0000 inches is a hand.
Maybe it's this way.
One other one besides
Crossway.
shake,
It's not
which I
7
thought
inches?
it's 4 inches,
Okay.
that I thought would be in Google Converter, but which was not, is the galactic year, which is the time it takes for the sun to go around
Yeah.
the Milky Way.
Yeah.
But
It's not a
You can-
Google converter.
you can Google it, but you can't Google Convert it. So,
Hmm.
Okay.
yeah.
Challenge accepted.
Okay. Well, I'm surprised at some of the ones I stumped you on. I'm really embarrassed for Jim about the quad, but that's okay.
Sorry. I've never
I'm
done
embarrassed for myself
Or-
about the shot.
I'm surprised.
That's true.
I think I just psyched you out about that
I wasn't.
somehow.
For once, I wasn't thinking about alcohol.
Yeah. Well, if it felt like 450 gigashakes, that's actually about what it was. Or you could just call it one Walkabout the Galaxy. Make a documentary movie about our show and then write a review of the movie on IMDb. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, Walkabout the Galaxy, where you can see most of our episodes, some of our bloopers, and all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter
At walk_the_galaxy.
and ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Thanks to our listeners in Ireland and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
We're the Astroquarks, signing off until the next episode of Walkabout the Galaxy.